Swayam Prabha. Digital India. Educated India.
Now another important parameter characteristics which is called California bearing ratio. Actually this is a penetration test for evaluation of the mechanical strength of road subgrade and base course. So the for soil mechanical strength one can measure. It was developed by the California Department of Transportation. That's why the name is California bearing ratio. So the test is performed by measuring the pressure required to penetrate a soil sample with a plunger of standard area. So some standard area, a plunger with a standard area, it penetrates within the soil. The measured pressure is then divided by the pressure required to achieve an equal penetration on standard crushed rock soil. This is the standard soil. Some standard soil, crushed soil, rock soil is rock material is there, and just compare the ratio. It's get the ratio value. Now here you can see this is a test result. For 70 psi, the penetration is 0.025 inch. So for 320 pounds per square inch, the penetration on the soil is 0.4 inch. This is the test result of on the soil. So penetration is 0.05 inch per minute. So here the soil sample is there and standard plunger, and it is being pushed at a certain speed 0.05 inch per minute, and the pressure is recorded, and for different pressure the penetration is calculated. Now here for different penetration and for different load, the penetration is calculated. Now the gold standard for severe, for 0.1 inch penetration, the pressure should be 1000 psi, and for 0.2 inch penetration the pressure is 1500 psi. This is gold standard, means this is the standard material for the test is the crushed California limestone. So that is the standard material, and for that, for if we apply 1000 psi pressure, the penetration will be 0.1 inch. When we apply 1500 psi, the penetration was 0.2 inch. Okay. Now for let us see for our test sample, it's for 0.1 inch penetration we needed only 220 psi. So for 1.1 inch, for 0.2 inch penetration we for 0.2 inch it was only 300 psi. So this is that our sample 0.1 inch and 0.2 inch penetration. This is the now values. Now for standard limestone it was 1000 psi the pressure was recorded. Here it was 1500 psi pressure was recorded, but in our sample soil we required very low pressure. That means soil is much softer than the standard value. So let us calculate the California bearing ratio. That is the ratio. So you can see simply for 0.1 1 inch, okay, it's 220 psi by 1000 was standard, so 0.22 or 22%. And for 0.2 inch from 0.2 inch penetration, the ratio is 300 by 1500, so 0.20, so typically 20%. So between 1.1 and 0.2 we will test both for 0.1 and 0.2 inch penetration, but the higher value of this will be taken as a California bearing issue. Okay, this is the system. So here the gold standard is already available, that is, and we have to compare with this with our present sample. So use 0.1 inch penetration unless 0.1, 0.2 is a greater. So greater of these two will be taken. Okay. So let us see the typical value. Now for it, these are in percent. For standard material, crushed limestone, it will be 100% because there will be same. Okay. For high quality crushed rock, very high quality, it's 80%. And for tilled farmland, which is very soft farmland, it's severe, very severe. Severe 3 means very low, very soft. So we use this our geotextile depending on the severe value, and also we select the stiffness of geotextile based on the severe value. So where severe value is low, so to enhance the strength of the system, we need stiffer geotextile. Okay, stiffness should be high. So for crushed California limestone, we may use a very flexible geotextile. Only strength is important. But here, to enhance the structural stability with the reduction in the severe value, we have to use the stiffer material. Okay, so that we will discuss later also. And for using the severe data, we can convert it to tensile strength, severe value. So here tensile force is TF, and punching force, it's a FP, downward force, and radius of severe plunger, this is the radius of severe plunger is R. Okay, R is the radius. So from there we can calculate the tensile strength, tensile force applied on the textile material, geotextile. So Fp by 2 pi R. Okay, this is the tensile strength. It's in kilonewton per meter. Okay, kilonewton per meter. And strain at failure, what is the strain? Initially in the plunger, this is the fabric specimen. Okay, and then when it is plunging downward and the fabric gets stretched, so A was the initial dimension, and after that it has become X. So X minus A by A, this is the strain at failure. Now, as I have mentioned, stiffness of fabric is also important, and stiffness is measured in the similar way that we have discussed, that Charlie stiffness tester, where the angle of inclination is 41.5 degree under its own weight. Okay, so inclined at an angle and the overhang length. Here we are not calculating the bending length. Here just simply overhang length is measured. What is the total level? Now here stiffness, okay, stiffness is converted here, measured by L by 2 cube by mass per unit area. That is the stiffness relationship here. And for subgrade CBR value, you can see very soft soil, less than 0.5 CBR value. Less than 0.5, we need very stiff, 15,000 to 25,000 stiffness. And as we increase the soil CBR value, soil strength, then we need little bit lower stiffness. So stiffness is actually inversely proportional to the subgrade soil CBR value. So the property is important in the field workability requirement for installation of geotextile. So this is very important. So for selection of geotextile, so what type of geotextile we have to use? First we have to test the CBR value of the site soil. Okay, if the soil is very poor or California ratio is very low, CBR value, the stiffness of geotextile required is very high. So we may need, that's why for very soft soil, we may need the heat bonded, thermal bonded calendared geotextile where the soil is very soft. Now, graph test is the construction survivability test. So we normally test in apparel textile, basically the strip test, but for geotextile, it is the graph test which is very important. This is especially for separation application. Okay, in the paper. So 25 mm narrow width, you can see that 25 mm narrow width grit are used. So here this width is 25 mm, but the fabric width is 100 mm. So that narrow width grit is used. Loading rate is given 300 millimeter per minute. This is standard method, and this is used for non-woven geotextile. And this for non-woven geotextile, the effect are more than the woven geotextile. And tensile strength is expressed in kilonewton. And here the sample is partially grip clamped. Okay, stress is not propagated on the entire width of the specimen, and which simulates the actual application of geotextile during the construction. Now let us see, this is the condition. Here a geotextile is being placed, and over which the stones are placed. Now here when the load is applied, load is being applied on the middle, on the top stone. The top stone will try to penetrate in between these two stones at the bottom, and they will be these stones will be pushed lateral, and due to the grip, this is the grip point where the bottom this two stones are in connection with the fabric. They will be pushed sideways, and which is simulating the grab strength. Okay, now try to see the calculation here. Here, let us assume the diameter of the stones are same d. These are the diameter of the stone. The graph tensile strength is required to design the geotextile for separation purpose. When the pressure is applied to the upper stone, which spreads the two lower stone laterally, they will try to. As a result, the tension is mobilized on the geotextile, which is actually equivalent to the graph tensile test. Okay, this is actually simulating the graph tensile strength. Okay, now here when the load is applied, this top stone is taking this place. Now initial graph this gauge length will be Li. Li is the initial length. So let us see the initial length, assuming that the half is connected. So this is the d by 2, and so 3 multiplied by d by 2 is the initial length. And after the penetration, the length will be d by 2. So LF will be, this is Li. This is Li. This is LF. LF will be d plus d by 2 plus d by 2. This is the, so lateral deformation will be, total deformation will be LF minus Li. This is the actual deformation. So we can see here is the, it's simulating the graph tensile test. Now diameter of stone is d, initial length is d by 2 plus d by 2 plus d by 2, and final length is this one. So without any stone breakage, so we are considering there's no stone breakage or slippage. So normally there is a slippage, but we are assuming there is no slippage. The maximum strain in the geotextile can be expressed as LF minus Li by LF. So LF final, this is LF final length is d, this d plus d by 2 plus d by 2. So this will be d plus 2 multiplied with d by 2 minus initial length was this, okay, divided by the initial length. So it is 1 by 3. So 33% is the strain. The theoretical maximum strain is the 33%. Now there is a relationship proposed by Giroud in 1984, which is actually, we can, from there we can calculate the tension required graph strength required on the textile material. So textile material graph strength is T required. AP is the applied pressure, whatever pressure we are applying. dV is the maximum void diameter. This is the maximum void diameter here, which is actually calculated to be approximately 0.33 D. This is the maximum void diameter within the stone structure, and average stone diameter is dA. Okay, this is the typical relationship, empirical relationship, and from there we can calculate the required graph strength, and also factor of safety we can calculate. Now let us see this numerical. the tire inflation pressure is 450 kPa. That means that is the pressure which is applied on the geotextile. The average stone diameter is 30 millimeter. Assume the geotextile is placed beneath the stone base coats, that is okay. Calculate the grab tensile strength of the geotextile. So what will be the grab tensile strength? Assume 60% of the total ultimate grab strength will be mobilized. That means the strain is not mobilized 100%, only 60%. Rest 40% will be slippage, stone slippage. Now, ultimate grab strain is 33%. So 33% that we have already calculated earlier. This is the 33% ultimate grab strain, and this is 33%, and then mobilized grab strain will be 60% of it, okay? Because 40% is slipping, slippage is there. So mobilized grab strain is this, and we know this relationship. So this is 0.198, and volume, the volume is 0.33 multiplied by dA, that we know. So dA is given, diameter of stone is given. So from there we can calculate 450 is the pressure. Here is the diameter of void square, and so from there we can calculate the required grab strength of geotextile, 8.73 Newton. The Swayam seam strength of geotextile, so that as we have discussed, so from there, because it's a normal roll size is 3 to 5 meter, and length is maximum, it's approximately 100 meter. That is the roll size. So, but in the road construction, we need much more dimension. So there are the different types of swing is there. Seams stitching is the single stitch, double stitch, J seam, butterfly seam. These are the different type of seams available. So tensile strength is actually the seam efficiency is calculated by the formula seam strength divided by strength of the virgin material. So strength at the seam position, so that the ratio is the seam efficiency. So at the seam TG, so T seam means wide width seam strength, and TG is wide width geosynthetic or geotextile strength without seam. The ratio is the seam efficiency. Next, coming to the most important property of geotextile, which is hydraulic property. So first characteristics of geotextile is the apparent opening size, AOS. Then cross plane permeability, which is cross plane means the liquid water penetrates across the plane. In plane permeability that we have discussed, it will be penetrating along the plane. Gradient ratio is another important characteristic that we will discuss. Long-term permeability. So apparent opening size, as per ASTM, we use the dry method with a glass plate. of uniform size. So several uniform size glass beads are used here, and then we used to sieve the uniform glass beads through the geotextile. Okay. See, this is the main advantage, that it's relatively faster compared to other methods. Now, dry sieving method, the wet sieving method is also there, but dry sieving method is that you first have to take 50 gram of smallest glass possible, let's just say 75 micron glass, and then sieve 10 for 10 minutes. 50 gram we have taken, then percentage of glass retained on the geotextile, then we have to calculate the percentage of glass retained, and then repeat. We just keep on repeating till the percentage of glass bed passing through is y% or less. So we keep on doing, and we have to increase the higher size. So gradually we increase the higher size. So, and graph is plotted. So just see the graph. There is a graph plotted. I'll just show you the. These are the different types of sieve. Okay. Now, this is this type of graph is plotted. Okay. First, we start with the lowest particle, so say 75 micron size, and then we get the percent. What is the percent retained? So this is the. Now here gradually we increase the, so percent final, that means percent. What is the percent? It's moving out. So here say 15% is coming out. So gradually we increase the particle size, and this glass beads are of equal size. So this is the instrument where sieving taking place. Now, what is the application? So in hydraulic condition, now you can see here, this is O90. O90 means 90% of holes, okay, in the geotextile are smaller than this number, this value. So 90% of the holes are smaller than O90. So if O90 is say 200 micron, that means 90% of the holes will be smaller than 200 micron. And D90 means 90% of the particle. D shows the particle diameter. O means opening of the geotextile. So D90 means 90% of the particles in the soil have a diameter smaller than this particle. So 90% of say D90 means say 100 micron. So 90% of the particles are smaller than 100 micron. Okay. Now, when the material is placed, the geotextile is placed on a soil condition to retain the soil. So in where hydraulic condition is less demanding, there is no wave, no disturbance in the flow. Only simple, very slow, streamlined flow is there of water. The diameter of the largest textile hole can be 5 times of the largest soil diameter. So O90 equal to 5 times of D90. That means we can have very large opening. Okay. very large opening when the condition is less demanding. But in case of turbulence, difficult hydraulic condition is there, where in that case O90 should be equal to D90. That means when the disturbance is there, so wave is there, okay, liquid it's flowing at very high speed. In that case, our conditioning should be O90 equal to D90. But when the situation is less demanding, very smooth flow, then we can have larger ports. Always our idea is to have larger port size possible, larger port size of the geotextile possible, because we need to allow the water to flow smoothly. There should not be any water logging. At the same time, soil loss should not be there. Okay, so difficult situation is there when under wave attack, where soil is loosely packed. So soil is not strong, so loosely packed soil. In that case, soil loss chances are there. So in that case, we have to use the difficult hydraulic condition. So, and when soil is of uniform particle size, that's important. If soil is normally, in case of soil, we don't have uniform particle size, different particle size. In that case, we don't need this condition. Okay, but when the soil is of uniform particle size, then it is actually unstable. And where hydraulic gradients are high, very high pressure, hydraulic pressure is very high, in those cases also we have to use the difficult hydraulic condition. Now the filter designing criteria is that the main criteria is that the fine soil particles should not be lost. Okay, that is the first criteria. And the pore size should be large enough for water to flow through the geotextile freely. So that's important. Now let us see, let us consider one geotextile. This is a geotextile, only one pore, let us consider. This is one pore. Now these two criteria, if you see, they are just opposite to each other. If we want to stop the fine soil particles from going out, so we have to use very compact structure with a very low pore size. But at the same time, pore size should be very open for water flow. So initially, suppose a soil particle is there with a large particle and small particle mix. Okay. Now initially there will be some piping that we cannot avoid for some time, but after that, when the stability is reached, equilibrium time is reached, then there will be a structure formed, stable structure formed, and through which water will flow through easily, but soil particle, even smallest soil particle will be reached from this. This is the basic structure, and there are different limits available. So O90 less than equal to 85. It's of soil, it's a granular soil, piping limit is there, and permeability is O90 is more than D15. So that's the limits. And the filtration, main function of filtration is the movement of liquid through the geotextile. So liquid movement should be there, free movement should be there. Okay. Otherwise, liquid clogging is liquid storage. If we stop the liquid, that means the total structure will get damaged. Okay. So main purpose, as I have mentioned, adequate permeability should be there. So open structure has to be there. And to retain soil, the tight structure is required simultaneously, which is not possible. So that we have to optimize this structure. And third factor which involves long-term soil geotextile flow compatibility. Okay, and should not excessively clog during the lifetime. That we have discussed already. Now, so it's a flow limit with limited soil loss. So soil loss has to be there initially, but it will be limited soil loss. And permeability, some of the geotextile used in this purpose are relatively thick and compressible. For this reason, the thickness is included in the permeability coefficient. So permeability coefficient, when we measure, we use the thickness. Okay. So permittivity is defined by this relationship, permittivity equal to the cross plane permeability coefficient Kn divided by thickness of the geotextile. Now, when we use this permittivity by using the thickness, we may sometimes get actually misled. So this is misused by modifying the permittivity result. Okay. Now let us see by this relationship, this example, the water flux, that is the flow rate, gallon per meter by per square feet of the two products A and B, 100 each, and permittivity of these two products are same, 3.3. So using this permittivity value, we can actually, the designer can predict the flux. So flux is important for actual application of geotextile, because how much water is moving through. So permittivity, if we can give, then if we can provide, then we can compare these two products A and B, because they are equal, they are at par. But these two products are of different thicknesses. One is 20, another is 100 mils. Now, the problem comes when we use the permeability by using the thickness value, then we get altogether different values, permeability value. So that is actually not, this permeability value is actually not reflecting the flux which is actually used in the design. So designer's ability to compare the geotextile is lost here. So permittivity is the correct index test because it allows the designer a direct comparison of flux between the material. So higher flux means higher permittivity. Okay. So soil retention and piping we have already discussed. So piping means the soil which is going through the passing through the geotextile material, but after certain time it will the structure will be stable, but even after that if the structure is unstable, then it will create a void. This is the cavity will be created and which will make sometime, so there will be catastrophic damage of the failure of the structure if it continues. So that we have to check. Now cross plane permeability test. So you can see this is the instrument where the water height, constant water height is maintained by the water overflow arrangement. So water inlet is constant, so water overflow is there, so we can maintain the constant water head, and the manometer before and below and above the geotextile specimen is two manometers are there, which will show the pressure difference across the plane, and water outlet we can measure the water flow. So here 50 millimeter head difference between the upper and lower surface. So here we can maintain the 50 millimeter head difference. At that particular head difference, through the opening of 25 millimeter diameter, how much liquid is water is flowing, that we measure. So volume flow rate is basically kept between, it's more than 1 liter, okay, in a given time, which is more than 30 seconds is measured. Temperature correction needs to be applied. Finally, I is the gradient ratio. Here gradient ratio is the water head divided by the cross section. So the total water head here divided by the cross section, so thickness of the material. Thickness of the material. Because water flow in this cross direction, that's why we take the thickness. Okay. This is the gradient ratio, and we can calculate the from this equation. Kn is the permeability coefficient, which is in meter per second. Delta H is the water head difference. A is the area of flow. Permittivity, psi is the permittivity, and T is the thickness. So using this relationship, we can calculate the flow rate. Okay. So Q is the flow rate. Now let us try to solve a numerical. 500 milliliter of water collected in 300 seconds under 50 millimeter head of water. The thickness of the geotextile is 0.65 millimeter. Diameter of opening in the permeability device is 25 millimeter. From there we can calculate the area of the flow. calculate permeability coefficient Kn and the permittivity. So using this formula, flow rate equal to 500 milliliter per 30 seconds. So this is 1.67, 500 divided by 300, 300 second, 1.67 milliliter per second. So you can convert it to cubic meter per second. 1.67 multiplied by 10 to the power minus 6 cubic meter per second. Then area, cross sectional area, pi by 4 and 25 millimeter means 0.025 meter. So from there we can calculate the area is 4.91 multiplied by 10 to the minus 4 square meter. Everything we are converting into meter. So water head is 50 millimeter, so 0.05 meter, and gradient ratio is water head 50 ratio with the thickness 0.65, 50 by 0.65, 76.92, and from the relationship we can calculate the permeability coefficient Q by IA, which is 4.42 multiplied by 10 to the power minus 5 meter per second, and permittivity is Kn by T, which is 0.068 per second. Okay. Next is similar numerical on cross plane permeability testing. Only data is changed here. 800 milliliter water is collected in 200 seconds under 40 millimeter head. Thickness of geotextile is 0.55, diameter of opening is 35 mm, and permeability coefficient and permittivity similar way we can calculate here. So permeability coefficient is 5.72 multiplied by 10 to the minus 5, and permittivity is 0.104 per second. Another method, which is a modified method of the cross plane permeability. In cross plane permeability, we have seen the water head is kept constant, okay, but in falling head, which is close to normal application, where water head may not be always constant, so water head changes with the time. So same it's simulated here. Okay. Sample. So here actually short soil sample connected to a stand pipe. So diameter of stand pipe depends on the permeability of the test soil, and the test can be carried out in a falling head permeability tester. Before starting the flow measurement, the soil sample is saturated and the standpipe are filled with bare water for a given level. So this is the system here. Now here the soil particles are there on the both sides of the geotextile. So geotextile with a cross section A, and initial height at the standpipe is there. Okay. Water column, cross section area is small a, initial height is 80. After certain time, water head is HF, okay, it is reached HF, and water outlet is there. This is after testing, but here the drainage holes are there. The test then starts by allowing the water to flow through the sample until the water in the standpipe reaches to a given lower limit, which is HF. So lower limit is HF. Let me see. Okay. The time required is measured, and on the basis we can calculate the permeability using this relationship. So permittivity, the permeability is using this formula. We can calculate the permeability where the heights, initial height and final height is required, and area is required. Kn is a permeability coefficient. T is the thickness of material. A is the area of water column above the geotextile, and A is the area of flow. So water column area is there given. This is water column area, and area of flow is larger here. That there is cross section of the geotextile here. Area of geotextile, and H0 is the initial height, and final height is given HF. Typically we keep 80 millimeter and 20 millimeter respectively, and we can calculate it. And delta T is the time required for water head to fall from H0 to HF. The next method is in plane permeability, okay, which is used for basically for drainage purpose, drainage application. Here the gradient ratio is the water height difference. This is the delta H is the height difference from, but in place of cross plane permeability we used the ratio of water head divided by thickness. But here, as the water is flowing from one end to another end, so the travel distance is there in the denominator always. So here it will be length L. Okay. So typically we keep the gradient ratio 0.25, 0.5 and 1 gradient ratio. We perform the test. Normal pressure is applied. Minimum size of the specimen is a 300 millimeter by 300 millimeter. And geotextile should be sandwiched between two thick rubber sheets to prevent any leakage, so that to ensure that liquid flows through only the in plane direction. So constant head, this is constant head test. So these are the relationship where Q is the rate of flow, cubic meter per second. Kp is the in plane permeability coefficient. I is the gradient ratio. Delta H is the head difference. L is the length of the sample. W is the width of the sample. And W and T means cross sectional. So the material, this is the material test specimen. here this is L, this is width, and here is the thickness. So the water flows through this cross section. That's why cross section area is W multiplied by T. T is the thickness of the specimen. Theta is the transmissivity. Okay. Now let us try to calculate the data from the in-plane permeability, in-plane transmissivity flow test on geotextile is given below. Calculate, these are the data given below. Calculate the transmissivity and in-plane permeability coefficient. The 2 liters of water were collected in 120 seconds. Thickness is given 3 millimeter and width and length are 400. So 400 by 400 is the specimen size. So let us see. First calculate the I value. I is 400 is the length and the head difference is 400 millimeters. So I will be 1. And quantity, the water flow rate 2 liter per 120 second. So this is liter per second. So we can convert it to cubic meter per second. 1.66 multiplied by 10 to the minus 5 cubic meter per second. And Kp is using, we can use the this relationship to calculate the Kp Q by IWT. Q divided by IWT. That means Q value is given. I is 1, W width is 0.4 meter and T is IW thickness is 0.003 meter. So 3 millimeter is the thickness, so meter. So we get the Kp value is 0.01383 meter per second, and theta is, using the above relationship, 4.15 multiplied by 10 to the minus 5 square meter per second. Next numerical, only data is changed here. 1 liter water collected in 90 seconds, thickness 2 millimeter, width and length 300 millimeter, head difference 300 millimeter. Again, the I value will be 1 and quantity of liquid 1.11 multiplied by 10 to the minus 5 cubic meter per second, and Kp value we can calculate it using this formula. It's 0.0185, and theta we can get 3.7 multiplied by 10 to the minus 5 using the relationship. And there is another flow possibility, which is a radial flow possibility, where the geotextile is there, okay, and suppose at the center somehow water is coming, liquid, and water has to flow out. So for that, the radial in-plane flow is apparatus is there. So here you can see at the center the water is being fed. So from there we can calculate the theta permeability and where R2 and R1 are the outer and inner radius of the specimen. So this is the system where water is supplied from the center at the certain water head, and we can calculate the, so geotextile is here in the annular shape. It's a similar to that of the cross plane permeability we have already discussed. Now gradient ratio test. Here this is basically used for the soil, but with the geotextile also we can use. Here we can see the similar instrument is used as we have used for the cross plane permeability. Water head is maintained at certain level. Now here we can see the 50 millimeter soil is there, and that head difference is calculated for a certain water flow rate. And another case, that 25 millimeter soil and plus geotextile, that head difference becomes H1 minus H2 will be that difference, and here H2 minus H3 will be the only soil. Only soil is H2 minus H3, and with soil and geotextile H1 minus H2. So the difference, the ratio is its gradient ratio. That means H2 minus H1 divided by 25. So H2 minus H1 divided by 25 is the thickness of the structure, soil thickness, and H3 minus H2 divided by 50 is the thickness of the soil. So that ratio is called the gradient ratio. So mass of pipe particle, mass by sample area. So that we can also calculate. For good compatibility between the geotextile and soil under steady state condition, gradient ratio should be less than 3. That means this ratio for if we remove the geotextile, ideally this gradient ratio is 1, because only soil. If we put a different condition, then it should be 1. But with geotextile, due to clogging, there may be certain disturbance in the soil structure, and presence of geotextile also increases the pressure difference. So this gradient ratio should be less than 3 for good to have a good compatibility between soil and geotextile. So this is the gradient ratio tester. Now, if we can see here, two materials, one is non-oven, another is oven. So this material after certain time, different time, so gradient ratio becomes stable. Initially for non-oven there is a disturbance, and initially there is a shoot up, and after that when the stable structure is formed here in non-oven, the gradient ratio remains almost stable. But for the oven fabric, the stable structure takes time little bit because of the uniform port structure in the oven fabric. That's why the stable equilibrium takes little bit time. So that means piping takes place through this area. Through this time. So gradient ratio test on two different types of material is shown on, this is on beach sand. Okay, you can see here the gradient ratio apparatus can also be used to determine the permeability coefficient over long time. Okay, so after this will predict that after long time how the permeability of the structure will be there. So this is this bottom line is a soil pipe. You can see initially there was a soil piping was there, but after certain time soil piping stopped. In that case, soil filter formed. That's in, that as I have told, the initially the piping will be there little bit, and then the soil filter will form, and then equilibrium is reached. Okay, so this is soil filter formation time. Okay, and I think we have come to the close the two of the course. We are end of the course, and hope you have got sufficient idea about the analytical approaches of textile testing, and you can please go through the numerical to understand the basic concept of testing. Thank you.